Hi, I'm Professor Johnson, and in this video we are going to be talking about the nature of atoms and molecules. So it's a lot about the basic chemistry that we're going to need for really to succeed in this course. Topics that will include both the structure and the function of atoms and molecules, the nature of chemical bonds, how chemical reactions are illustrated using chemical equations, and finally we'll look at some acid-base chemistry towards the end of the video. So this is your typical picture of an atom. It is a simplified version, but you may be familiar with the three main parts, including the protons depicted here in red, and the neutrons depicted here in blue, and then the electrons here on the outside. Now, when we talk about the different atoms, we're talking about atoms of elements, and each element is going to have its own unique atomic number. The atomic number refers to the number of protons in the nucleus. So this atom here would be helium because it has 2 protons. The atomic mass is really the mass of the atom itself. Now there are 2 main things that make up the mass. It's the protons and the neutrons, which essentially have an equal mass. Electrons also have a mass, but it's so small compared to these that you can just neglect it. And so it's really just the protons and the neutrons that are making up the mass. Now you may have heard the term isotopes described before. What isotopes are elements that have the same atomic number, so it's going to be the same element, but it's going to have a different atomic mass. So if it has a different atomic, or if it has the same atomic number, that means it has to have the same number of protons. But if it has a different atomic mass, that means that the neutrons must be varying in these structures. So when we look at the different elements, you can see here is a periodic table that typically describes them. We can look at elements having different energy levels. So the energy levels are really what is happening in each row. So this first energy level here that has these 2 gray balls that are the electrons, that's what's going to be the hydrogen and the helium, where their electrons are going to exist. In the second row then we have the next energy level, which is the second row here. In the third row then we have another energy level as well. Now the first energy level can hold 2 electrons. The second one can hold a total of 4 electrons, and then the third one can also hold a total of 4 electrons. The inside energy levels will always be filled first, and then you will work your way to the outside. And elements want, you should say that in quotation marks, but they want their energy levels to be filled. So they'll try to fill them in one or another ways, and that's how we'll get the different chemical bonds. It does get more complicated when you get down here to the transition elements and the rest of them as far as how it gets filled. But for the most part, just know that these want to have full, which means hydrogen is going to want to get to have 2 total electrons, whereas most of the other ones we're going to look at are going to want to have a total of 8, which is commonly known as the octet rule. So what are the elements that we're most concerned with? Well, there's really 4 that are really common in biology. The first one is carbon. This next one is oxygen. Then we have hydrogen. And finally, nitrogen. Now, we focus on these because they're going to be the most prevalent elements that are in our body. It's going to make up the majority, the elements that make up the majority of our mass. So here's what their atom diagrams really look like. So you can see carbon has the first energy level. All of these, except for hydrogen have the first energy level occupied, and then we're out here in the second energy level. Now carbon is going to have four total electrons, so it needs to find a way of sharing 4 more to get 8. Oxygen here is going to have a total of 6, so it needs to share 2 more. Hydrogen needs to get 1 more to have its full shell, and then nitrogen needs 3 more to get its shell. We'll talk about how they can get these. First, a concept that you need to understand is the concept of electronegativity. Electronegativity is essentially how strong the different atoms hold on to their electrons. So you can think of 2 different ways that elements could lose their electrons, or could change, or could have a full outer shell. They could either lose it so that their outer shell is the shell beneath them, and then they would have it, or they could gain electrons. Now, the 4 most common ones are going to have high electronegativities, which means that they'll hold on to their electronegativities fairly strong. Now, if we look at how the bonds are going to interact, if you have 2 elements that are going to be drastically different, they're more likely going to steal them away. So if we look at the different electronegativities, we can classify them, the type of bonds that are going to occur between them. So you can have a nonpolar covalent bond where the electrons are being shared equally, a polar covalent one where they are being shared but not equally, and then ionic, you're going to have the electrons being completely stolen away from them, and so then you're going to have ions being formed. Common covalent bonds in biology are these that you see below here. So you can see with this one right here that I calculated, you can look at that hydrogen has a 2.2 and carbon has 2.55, so you'd subtract these to get the difference between them, and it's 0.35, so this means that this bond here is going to be nonpolar covalent. Now if you look at a different one like carbon oxygen bond, it's not going to be, it's going to be a larger one, so it's going to have actually a polar covalent bond that ends up existing. So this is what it looks like when you have covalent nonpolar bonds. All of these, because they're the same element, are going to be sharing them equally. So you can see that there's a number of different ways that they can share. So up here we have a single bond being formed, here's a double bond being formed, and here's a triple bond that's being formed between the atoms, and they're all sharing them equally. So we have their covalent nonpolar bonds. Now you can have the covalent bonds as well. So here the atoms are sharing them, but they're not sharing them equally. So oxygen has a slightly larger affinity than hydrogen, and it's large enough that you actually get these partial charges. So the oxygen has a partial negative charge because it's holding the electrons closer than the hydrogen, so that you get this partial positive charge. Now ionic bonds, like you would see with salt, sodium chloride, what's going to occur here is that chloride holds on to the electron strongly, sodium does not, so chloride is going to just end up taking the electron from it, and so now you have chloride with a negative charge and sodium with a positive charge, and this is how you typically would see these elements as they exist in a solution, for example. So sodium with a positive charge and chloride with a negative charge, and these are what characterize ionic bonds. Now hydrogen bonds are really a very weak interaction. So recall that oxygen here is going to be partially negative and hydrogen is going to be partially positive. So if you were to throw in another water molecule, you can see that these negative charges, partial negatives, can interact with the partial positives. And when you get this interaction, then you're going to have a hydrogen bond. So it's weaker than ionic bonds and covalent bonds. So covalent bonds are the strongest, then ionic bonds, then the hydrogen bonds. But these can be very significant when you look at their function as a whole. This is really what's responsible for giving water all of its different properties, and really what is going to make life on Earth possible, because water is a very important molecule for life here on Earth. So we'll come back to water in a moment when we talk about acids and bases, but I also wanted to briefly talk about chemical reactions. So if you look at a chemical reaction, typically they're going to be written as such, with reactants here on the left, products here on the right. So A and B are reacting to give you C and D. It could be A and B are reacting to give you C, or A reacts to give you C and D. It can vary in the ways that the reactions are going to occur. X up here is what's known as a catalyst. So the catalyst is something that can speed up the rate of the reaction. It won't drive the reaction forward or in reverse. So all chemical reactions, to a degree, can go in the forward or the reverse directions. Sometimes it's more favorable to go in the forward directions, and sometimes it's more favorable to go in the reverse directions. Now, the rate of a reaction and the direction that it ends up going can really be influenced by a number of things. So temperature can really increase the rate of the reaction. It typically won't drive the reaction one way or the other, but it does increase the number of collisions that can occur between different molecules, and thus the likelihood that a reaction will occur. The concentration of products and reactants can occur. So if you increase the number of reactants, there's going to be more collisions among the reactants that are in favorable ways, such that the products are formed. So if you increase the reactants, it'll drive the reaction to the right. If you increase products, it's going to drive it to the left. And similarly, if you decrease the reactants, it's going to increase the reaction to the left, while if you decrease the products, it's going to increase the reaction to the right. Catalysts aren't going to drive the reaction one way or the other. This is important. They're just going to increase the rate at which the reaction reaches equilibrium. So it's going to favor, it's not going to favor one or the other. It's going to stimulate both the forward and the reverse reaction when it comes to chemical reactions. So let's return now to acid-base chemistry. So recall that hydrogen bonds can form between water. In fact, one thing that can happen is that the water molecule can actually lose a hydrogen, and another water molecule can gain it. So when this happens, you have a hydroxide ion and a hydronium ion in solution. And this is occurring all the time in water. And the concentration of this is going to affect whether the solution is acidic or basic. Typically, it's going to be around a pH of 7, which is neutral, and that's related to what the concentration of the hydronium ions are in that solution. So pH is related to the negative concentration of hydronium ions. This is really a simplified version of just talking about the hydronium ions. So an acid is going to be something that donates a problem. So here we have HCl. This is constitutes your stomach acid. It's going to actually donate a proton to the water. So now you have an increased concentration of hydronium ions. A base, on the other hand, such as sodium hydroxide, if you put this into solution, there's going to be a number of these. And remember how chemical reactions, if you increase the hydroxide ions, you're going to drive the formation of this. So you take that proton from it, and now you have a water molecule. So this is essentially going to decrease the concentration of hydronium ions. Now, pH is how we typically signify this. It's really the negative log of the hydronium ions. So the hydronium, or the negative log, indicates that it's going to go in the reverse direction. So an increase in pH results in a decrease of the concentration of hydronium ions. Log is going to mean that it's a tenfold change. So a one-fold change in pH, if this goes from 1 to 2, this means that there's going to be a tenfold change in the concentration of hydronium ions. And you can look at the pH scale, and anything that's above 7 is said to be a basic solution. Anything that is below 7 is going to be something that is an acidic solution. So anything that donates a proton is going to be an acid because it's going to drive it towards the acidic solution. Anything that accepts a proton is going to increase the pH, so it's going to make the solution more basic. Now, one distinction that we haven't made is the difference between strong and weak bases. So a strong and weak acids as well. So a strong acid is going to completely dissociate in solution, such as HCl. So here you're going to completely lose the H+, which can then go to a water, and so you're going to have a pH change that's relative to the concentration of acid in solution. A weak acid then is something that's not going to completely dissociate. So you're going to have some of this in solution, but some of it is going to protonate and form this solution. So you can see that here, if you would have a strong acid, you would have more of a 1-to-1 formation being formed. This doesn't really show a strong acid, but a weak acid here is going to be something that gradually changes the pH. So here there's an equilibrium where as you keep adding protons, you're adding something to the side of the equation. It's going to drive the reaction this way, so you're not really doing as much to the concentration of hydronium ions in the water as a strong acid would. So it does this gradually until finally you've essentially used up all of your weak base, and so now it can go back up. So this would be how the pH is going to look more when it actually starts to lose its region. So a weak acid is going to, so this is the weak acid, it's going to have its conjugate base. So an example of this would be bicarbonate. Bicarbonate acid and bicarbonate. So bicarbonate is going to be the weak base that goes in this direction, and bicarbonic acid is going to be the weak acid that goes in this direction. So this H here, HA here is the weak acid. This H+ is its conjugate base. And that's it for this video. I will see you in class.